Okay, so I'm gonna go through the lecture slides very briefly, see where we stopped last time, and then we'll continue from there. So the idea behind idealization or behind this topic is how can we how can we simplify our structure so we can still analyze it using our equations that we basically went through in the previous three topics of bending, of shear, and of torsion. So this is, for example, on a real life structure, of course. So we see there's a bunch of ribs, a bunch of spars, lightning holes, etc. So if you want to go basically for this real life structure and want to simplify it, we need some assumptions to it. And with that said, we look at basically how we can dumb down this structure to something easier. And we said, look, first of all, we realized there are a couple of different components. We have the skin, we have the stiffness, we have the spars, and each and every component has a certain function in our structure. We say the skins can take either shear loads due to torsion, some bending. Stiffness can take up the tensile loads and the compressive loads, and the spars can also take both bending and shear loads. And then we said, okay, if we have bending, we basically just deform, either due to a shear force or due to a moment. And we say locally, if we look at a stiffener or strainer, the variation of the stresses are very small, so therefore we can assume that the variation locally is just a constant. So basically the variation here around the Z stiffener, we can basically just say this very small, and therefore just a constant. And same thing for the skin, because it's so thin, we can assume it's be a constant. Another thing we said as well is, well, we know that in the overall picture, the distance from the skin centroid to the stiffness centroid is going to be very small. So therefore, we assume that these two coincide as well. So very simply stated, we have our skins that carry shear stresses, thinners or stiffeners carry normal stresses. And we said, like, in order to simplify, what we do is we calculate the equivalent basically area. We call that a boom. And we say that equivalent area, all the normal stresses are carried by that area. So if you want to calculate the stresses, basically the force over area, or vice versa, if you want to calculate forces, we just do stress over an area. No, stress multiplied by an area. For the skin, we have basically two options. This second option basically comes in more importantly in the shear flow section. So what we can do today, we can either say it carries normal stresses or does not carry normal stresses at all. So only carries shear stresses. So of the two, the assumption of that doesn't carry any normal stress is most common. And if we assume that, then the skin thickness is set to 0. And this will be again shown up in the next equation that we talk about shear flow. So basically what we did, if we summarize everything in a figure, we went from the top figure to the bottom figure where the stiffeners and the equivalent, say, masses of the skins is basically lumped into one area that we call a boom. And we can calculate that boom areas using basically by looking at the stress distribution in the structure, real structure and an idealized section, and then comparing these two must be equal to each other, so therefore we can isolate the boom areas. And we did that, like I said, by looking at the stress distributions. We can look at this idealized structure and the real structure. For the real structure, we have to deal with the integral from 0 to b, the integral from this basically segment here, of course multiplied by the thickness. And we take that integral and we can come up with the moment distribution around 0.2. And if we do the moment distribution around 0.1, since we said the booms carries all the direct stresses, it's going to be just stress at the boom area 1 multiplied by the boom area 1 multiplied by the total distance, or the arm, in this case b. And then we can equate the two to one another, and then we can find out what we have one equation with one unknown, which is B1, and then we can figure out what B1 is. And then if we do the same thing, but then force balance, we can figure out what B2 is. And we did a quick example. We had a wind box, and we went from a say complex structure shown in A to our idealized structure. And as you can see is that we basically replace all the stiffeners shown here with just a lump of mass, boom 1, 2, 3, 4, 5, and 6. And then if you want to calculate the boom areas, we needed basically the ratio of sigma 1, sigma 2. But we know if we keep under an applied moment, we know that the stresses are equal to the moment over the Ixx over multiplied by y. We know that applied moment will be, of course, equal for every case. We know that the moment of inertia should be equal in all in the cases. And if we substitute sigma 1 and sigma 2 in the previous equation, we know that basically m and Ixx basically cancel out, so we have a variation of y1 and y2. So if we do that, we basically calculated the following boom areas. And that's where basically we stopped. No, we went one more slide further, and we said, okay, well, how does booms affect our equations? And we said, well, traditionally the equation itself does not get affected. The moments my and mx, of course, those cannot get affected either because these are applied moments. Locations x and y, again, these are locations, so they do not get affected either. So the only thing that basically got affected by our idealized structure is how we calculate the moment of inertia. Because we assume the thickness to be equal to 0, the 1 over 12 b cubed h cubed b or h cubed t, basically that drops, and then we have left over is basically the Steiner terms. And that's the reason why the moment of inertia for an idealized structure where we have booms is given by the summation of areas multiplied by the y distance squared, or area multiplied by x distance squared, and or area multiplied by x, y. And it's common to have, instead of area, we just say b. So that's also common. Okay. So with that said, we can continue where we left off. And the next equation that we're going to look at, or next topic, so we already looked at bending, and that got affected. So we have two topics left, is the shear and torsion. And today we're going to look at those later two equations, how they get affected. So for the shear flow equation, let's recall that in the most generic way. So this is our shear flow equation. Yes. And then we have another component, Sy, Iyy. And the last component was, of course, the correction shear flow if we have a closed section. So this will be our standard equation. So and then we made an important assumption in the beginning of the slide. So we said, okay, we have two options for the skin. It's either it can carry some shear loads, or doesn't carry any shear. So those are the two options that we have. So if you basically look at the second option, doesn't carry any shear, is where we also assume that the thickness of the skin thickness, let's call that TD, is equal to 0. So in this case, the skin thickness is represented here. Left it blank deliberately. So basically, if we assume that shear doesn't get any stresses, then this will basically disappear. But then we basically also mean that we don't have any shear stresses at all. But we do. And what it basically comes into is that the boom areas, we have to add the effect of the boom areas, By, to make it complete. So this is our most generic case. And then if we assume that the skin doesn't carry any stresses, this disappears, this TD basically goes to 0 and the integral drops out. And we assume that the booms between two panels, or the shear flow between two panels, Q is a constant, and shear can only increase when we basically pass over a boom. So we have another boom, and we have, say this is Q0, and then Q1 will be Q0 plus QP1. And that's basically listed in the second part of the equation. So in our, when we say that basically, when we have our skin panel, normally we had our thickness and our, say our shear flow would increase as we move along our segment. This is no longer valid. So when a boom area is, because we don't have any thickness, this basically drops to 0, and the only increases happens when we basically pass a boom area. So plus some Q here, and that's represented by basically the shear flow is the increase in shears equivalent to the boom area multiplied by the distance x or y, depending on if we have symmetric and x, y, and xy, sx and sy shear forces. So be careful when we basically do assume the skin to carry some stresses. So then the TD is no longer 0. So in this case, TD is not equal to 0. And then you have both the integral format and the additional contribution of the boom area. Then we can do actually an example. We can also see how much is affected by it. So we can actually, we did a previous example in the class where we calculated the shear flow of a C-section, and we can actually repeat those problems by replacing the cross-section by 4 booms, 1, 2, 3, and 4. And in this case, to make our life a bit easier, B1, B4s are given, 300 millimeters squared, and B2 is equal to B3, that's equal to 500, and SY is equal to 6.4 kilonewton. And then we basically, and we can basically calculate again using this formula the shear flow for boom or an idealized cross section. So by looking at the shear flow formula, we can immediately see that a correction shear flow is not needed because this is an open section. This part is 0. And if you look at the slide, it says the skin is only effective in shear. Basically, oh, sorry, this is incorrect. Carry some normal stresses, and this doesn't carry any normal stresses. A mistake on that. So carry some normal stresses. TD is not equal to 0, and doesn't carry any normal stresses. TD is equal to 0. And this makes a bit better, more sense, because this equation, how we derived it, it basically came from our direct stress equation. That was basically our generic version of this equation, where we basically substituted the equation or force, moment and shear force, relationship between that into this equation, and then we basically got out our shear flow equation. So if we assume it carries direct normal stresses or direct stresses, same thing, then TD is equal not to 0, and we only assume it doesn't carry any direct stresses and only shear, then TD is equal to 0. So this is the direct stress component to it, and this is basically, that will disappear either based on the assumption. So in this problem, the problem states skin is only effective in shear, and this would mean that TD is equal to 0, because it does not specifically talks about carrying normal stresses, therefore it's for you safe to assume it's equal to 0. So, and then we can do, repeat this, basically we can reduce that equation. So we have only an Sy given, so Sx is equal to 0. It's metric, so this drops, and this reduces to Q is equal to minus Sy Ixx to this equation format. Yeah.
So these assumptions, are these like predefined, or is it up to us to assume that they carry any stresses or they don't?
It will always be given in the problem. So words like it's only effective in shear. So the problem will state the following cross section is only effective in shear. So for you, it should be enough to state, or should be basically a trigger word that's only effective in shear, and therefore there's no normal stresses. And often the thickness is also not given, so you either assume T or just, but yeah, but it's given in the problem, one way or the other. Sometimes a bit more specifically mentioned, and other times a bit more cryptic, like it's only effective in shear, or it's effective in shear and stress. So you should basically deduce from that you should deduce that you can either use TD is equal to 0 or not equal to 0. So we can do the same problem. In this case, again, we have to calculate Ixx. Sy is given. So we know from the problem it's metric. So let's see what the distances are. So this is 200. And this is also 200. So we can calculate the moment of inertia. So Ixx, again, for booms, is nothing else than dy y squared, di by I squared. So in this case, we can use symmetry, so it's 3 times. We have 300 multiplied by 200 squared plus 500 multiplied by 200 squared as well. Let's see. solutions. Let's see. This is 1600. That's 800. 1600 by 200 squared. $40,000, 1600 to 40,000, 1, 2, 1, 1.6, 6400. See, correct series. 2, 6, 6, 7. So double check that, should be 64 10 to the power 6. And let me see. So Sy is given as 6.4 kilonewton. So that will become 6 10 to the power 3 Newton. So our equation will be something like this. Qs. Okay. So this becomes 6.4 10 to the power 7. Right?
Yeah, to the power 7.
Yeah, 6.4 to the power 7. Yeah, perfect. Yeah, I think I chose it for this to drop out. So this becomes 10 to the power, basically we get 6.4 10 to the power 3 divided by 6.4 10 to the power 7. And then the summation of by squared, by. So this, to reduce it in complexity, we get 10 to the minus 4 by. Summation of by. So that will be our equation. And again, I have to state there's an open section, so we either start at 0.3 or 0.1 or 0.4, because we know that the starting shear flow is there 0. So let's start at 0.1. We get Qs Qs 0.2 is 10 to the minus 4, and then the summation of the boom areas plus y. In this case, we basically move past one boom area, so that's b1, and the y distance is to the centroid. So the centroid y location is on this center line. The x location is somewhere here. But we don't need that because we're only interested in this equation, only y appears. So we don't have to calculate the centroid. And we know based on the problem that it's going to be 200. So it's going to be b1 times 200. And we can substitute for b1 300. So we get Qs12 is 10 to the power 4 minus 4 multiplied by 300 multiplied by 200. So this becomes 600, 60,000 10 to the minus 4. So it becomes 6, right? Yeah. Newton millimeter. And what we know is that at this location, this segment is equal to 6 Newton millimeter, and it will remain constant. So the shear flow does not change until we pass another boom area. Then we can calculate Q23. So get Qs23. That's of course the starting point, Qs2. And because it's constant, we know it will be just equal to 6 plus 10 to the minus 4 summation b times y. So this becomes 6 plus 10 to the minus 4 multiplied by 500 times 200. So this will be 100,000, 10 to the minus 4. So it will be 10, so we get 16. So that means that this following segment is equal to Newton millimeter. And then of course we can calculate the third segment as well. And what we'll see is that in this case, y is only singular, so it's not y squared. So it becomes crucial that you use the correct sign for y. So if you do actually Q2 QS34, you will start with 16 and I made a mistake. I'll get to that as well. Yeah, just correct that mistake. So I forgot the minus sign here, if you notice correctly. Because the equation is still sy minus sy summation of dy. So I forgot the minus sign there. So which means that this is a negative, that this is not a plus but a negative. So we get minus 6 minus 10, so we get minus 16. Here we have minus 16 minus 10 to the power 4. And then multiply by the boom area 500, multiply by minus 200. Because, like I said here, this y is singular, so the coordinate does matter. And it's because it's below the centroidal axis, this coordinate is negative 200. So, and then if you do this correctly, we'll come back to minus 6 Newton meters. So if you do it again, here we get 6 Newton millimeter. And again, what we stated earlier, we assumed it will go from 1 to 2. We got negative 6. So basically what that means is that our assumption that 1 to 2 is basically opposite. Else we will get a negative number. So if we would redraw it like this, it will be just 6. Let's do that. So it means that our shear flow went opposite than what we assumed. That's the only thing what the negative shear flow number means.
Could you show where the SY is applied to?
SY doesn't matter where it's applied. It's given as applied through the shear center. So it doesn't create any twisting in moment, but it will be up in opposite the positive direction. As otherwise it would be a negative number.
So does it matter if the SY is located to the right or to the left side of the shape? Is that going to change the shear flow or something?
No. Up and down will change it.
Up and down.
Yeah. The location does not change the shear flow directions. And we always assume in most problems, you assume that it's just acting through the shear center to make your life easier. Because then you don't have to deal with the twisting of it. Okay, so let's redraw this figure and let's recall what our previous figure looked like when we did it without the boom assumption. So as you can see, actually now the shear flow equation becomes actually easier because it just becomes a summation of areas of the area B multiplied by the distance y. So let's redraw some of our figure. This was our cross section. And with the boom areas, we got uh, 6, this was 16. And if you recall correctly, when we did this problem in our, let's say, in our fear section, uh, in our safe section, we got something like this. So the shear flow would linearly increase bottom and top flange, and will be quadratic on our vertical flange. So yes, we made our life easier, but we also came at a cost that we lose accuracy in our solution. So if you would calculate the maximum shear flow for our second case, we always know that's located somewhere in the centroid. Here we got Q max, say real, will be larger than the Q max ideal. So what that basically means is that our original assumption that we had 4 boom areas is not an accurate solution for our problem. There are a couple of ways how you can improve upon that solution. Is instead of having 4 booms, is by increasing the number of booms. So we could add another one here and 2 more here. So what that will do is the same thing. You will have your constant shear flow between booms, and here we'll basically add another step in it. Similarly, here we will add another step to it, and here of course will decrease. And you can see if we increase number of booms, we'll go to the real structure. As well, we can somewhat in a simple manner say it's equivalent to a finite element code, where we increase the number of elements, we can approach the real solution. But
the booms added should have the same area as the.
You have to calculate again what the equivalent boom areas are. So if you add more booms, your B1, say 1, 2, 3, 4. So B1, 2, 3, and 4 will no longer equal those. Because the boom areas, again, what we did is this contribution, right, was B1 was equal to TD times B over 6, 2 plus sigma 2 over sigma 1, right? So your skin thickness will probably be the same if you go from real to ideal, but this width over the segment now changes, gets smaller. So you have to update both the booms and then re-update the solution procedure. So it's basically an iterative process. If you increase the number of booms, you have to recalculate what the boom areas are. Okay. I'm going to show an in-class example. This is actually a good example for you guys to do at home. So I'll discuss this one actually next lecture, because I want to give you guys an opportunity to do it before we go through it. So yeah, so what we said earlier as well, for the skin, we assume it can carry some normal stresses, it cannot carry any normal stresses, and that effect has it on the if TD is equal to 0 or not equal to 0. So this was our previous example we actually did quickly on the whiteboard. So you could redo the same problem, but using a normal shear flow approach, where we assume a thickness of 3. and then you can actually calculate how many booms you have you need in order to get within 3% of the maximum shear flow. This will be a very I think I gave this previous years as an exam question. So in this case, what you have to do is you have to go to that iterative process where you calculate the boom areas, and then you can calculate what the maximum shear flow is. So I think this is also a book problem. I don't remember which book problem it is by heart, but it's actually a very good problem to do. It's a closed section and requires you to using booms. And in this case, Maxon does a weird trick, so I want to see if you guys can actually figure it out on yourself, and we'll discuss this in next week's lecture. I would highly recommend you guys do this at home. Just first of all, it's good practice. It's in the closed section, so you have to make a cut. So the location of the cut will be important. Finding all the shear flows are important, and then finding the correction shear flow as well. It's important. So in this case, you would assume that TD is equal to 0 in this case. So you would just go with this equation here. You know that Sy is given as 10 kilonewton, Sx is not given. So this actually reduces to the previous equation that we had on board, which was equal to Sy Ixx multiplied by Bi Yi plus the shear flow, correction shear flow that we have.
Just by looking at the problem, can we say that the shear flow will be 0 between 4 and 5 and 1 and 8?
No.
Does it look like it? Or?
No. Will not be 0. It will be 0 if you make a cut there. Yeah. But then you have the correction shear flow. And that will be non-zero.
So in the cases where it's 0, the axis of symmetry should be in the y-axis, and the loading as well should be in the y-axis.
Yeah. And the loading should be actually at the symmetry plane. Yeah. So not just at the y-axis. So for example, let's go to the. So in the exam, and also on lecture 16, why the shear flow or the correction shear flow was 0, and we can immediately state it. So if you lecture 16, this was the cross section. Yeah, plane of symmetry here, and our shear force was acting at the plane of symmetry. So that's the reason why it was 0.
If it's shifting left or right, it won't be 0 like that.
No. Because if you shift left and right, say this one is, let's do a box, it's easier to draw. So if you have this, here we can make the cut at this location. Now shear flows will go something like this, based on symmetry, right? So if I now take the moments around this point, then I have symmetric shear flows. Here, if you make the cut, will be something more complex, because say you make the cut here, will go like this. This will be quadratic, correct? Quadratic like this, and like this, and something like this. And if you now take the moments around this point, there will be two counteracting shear flows, but they're not equal in magnitude. So one of them, there will be a correction shear flow to it. So what I said again is like also in the exam, what you had was this shape, right? Just draw, make the cut, and draw how it looks like. And you can often see if you can reduce the problem complexity or not. So there's always a good start to do. Second thing, what you always have to do is, by looking at it, realize if it's an open structure, a closed structure, or combined open/closed. because the solution approach will also vary on that. Okay. And last thing for torsion, that's actually simple. It doesn't affect the equations. Because if you remember in torsion, what we had was T is equal to 2 times the enclosed area times Q. And it doesn't really matter if the enclosed area consists of a skin or consists of booms. The enclosed area still remains the enclosed area. So in that case, basically boom areas does not affect anything in calculating the shear flow, because it's just multiplied by 2 times the enclosed area. Okay. So that one is very simple. So just do it as is. So another topic that we're going to go for, if you actually look at our structure, is what we did so far is we always have assumed, for example, in this one, it's just one cell. So there are no different components, compartments in the problem. And if you saw earlier in our problem when we started doing our analysis, this, for example, is a 3-cell problem. So you have one cell here, which is fully enclosed, second cell, and a third cell. And in this case, this will be a double cell problem, 2-cell problem. So, and for this one, we just calculated the boom areas. But if you want to calculate the shear flow in this case, you have a multi-cell and both of them are closed. So you have to basically apply the theory twice. You have to make 2 cuts at 2 locations, calculate the shear flow twice, etc. So that's the next topic that we will talk about, is how to deal with multi-section problems. And we're going to start in this case, not with normal stresses and shear stresses. We're going to start with torsion because that's basically the simplest. So what we said with torsion is if we apply a torque to it, we basically create a twist angle or rate of twist corresponding to that. So one of the key assumptions that we make for multi-section is if the section twists and deforms, it twists as one whole structure. So in this case, if one of the cells twist, they must all twist the same amount of proportion. They must twist the same amount. Because of that, we can state that the torque that we just said is equal to 2 times the enclosed area. We also state that each individual cell, if we calculate the amount of torsion it takes up, must equal the total torque applied to that structure. So in this case, if we have 3 sections, for example, cell 1, 2, and 3, and we calculate the torques of T1 plus T2 plus T3 must all equal, we sum that up to the applied torque. So combining those 2 equations, the equation for torque and that total torque must be equal to the summation of the individual torques, we can state that the total torque must be equal to the sum of 2 times the enclosed area. So we can take the 2 constant out of it, and then I goes from 1 to n number of cells. And the last thing that we also start with torque and torsion is it twists an angle, twists a body, and that twist we can either represent by the total twist or the rate of twist. So d theta dz. And if we recall that equation, that's equal to 1 over 2 times the enclosed area times the shear modulus, and the integral of q ds t. And we also state if the cross section of a multi-section torques or twist, rate of twist of the individual cells must be equal, or at least to the adjacent cell. So that means that the theta dz for cell 1 must be equal to the theta dz of cell 2 must be equal to the rate of twist, the theta dz of cell 3. And what becomes important now is that if we solve this shear flow problem, let's actually go to the whiteboard. So this repeated what was on the slide. If we go to the shear flow problem and we say we have three different components, three individual torques that form the total torque. So each of these will create a shear flow. Let's try them like this for now. It's important to draw the shear flows of each segment and then see what the effect is on adjacent members. So in this case, we'll have Q coming like this. On this side of the wall will go up because you still have to maintain that counterclockwise rotation. In cell 2, we draw that in blue, we'll have a shear flow going like this, going down, going to the right, going up. And then for cell 3, we'll have also a shear flow going to the right, then going up, and on this right hand side of our second cell, it will go down, while on the left hand side of our second spar, it goes up. So now if we do our equations, these two segments you have to be extra careful for. Because in this segment, one goes up on one side and the other side goes down. And we'll have to do a small problem and where we basically can use those different cells and different rotations and how we can solve that. So let's do a small problem. We have a square beam or square cross section, which is three sections. This is length A, and this is length B, another B, and this is also A. And we have a total torque of T applied to it. See, counterclockwise, yeah. And now we can basically apply, we also assume thickness T everywhere. Now we can see how this, let's call this equation 1 and equation 2 apply to our problem. Sorry, equation 1, equation 2, and 3 apply to our problem. So first of all, the best thing to do is to draw all the different shear flows into each cell. Let's see if I can find some colorful. Okay. So let's draw the shear flows, and it doesn't matter which cell you start with, as long as you remain consistent. So there will be cell 1. We'll have Q2 and then as last the purple, and this will be Q3. And we know by definition that the torque and the individual components summed up must equal the total torque. Okay. And we know that the theta dc in cell 1 must be equal to cell 2, and the theta dc of cell 1 must also be equal to cell 3. So now what we can do is basically use these two equations to see what we have. And we can start with cell 1. Cell 1. And we can write the theta dz, rate of twist of that cell. It's 1 over the area. Here comes the area. And we assume a constant shear flow or shear modulus, so we can take G out of it. And then we also set T is equal to T everywhere, so we can take those out of it. And then we get is Q ds. So what does this mean? This is the integral around the cross section of cell 1, and the ds part is nothing else than the total distance traveled, so the segment 1. And we also know from our torsion section is that torsion yields a constant shear flow. So what this means is that Q is basically a constant, so we basically have to just multiply by the corresponding distances, because the integral of ds becomes s, and in this case goes from 0 to a, so that's nothing else than a. In this case, from left, this is 0 to b, so this becomes b. This again 0 to a, so it's another a, and there's another b. So let's write that out. We get 1 over 2 times a1 gt, and then what we get is, write out the integrals, 0 to a q1, this one, ds plus 0 to b q1 ds plus 0 to a q1 ds plus 0 to b q1 ds. So that's basically the shear flows due to the internal T1, cell 1. So, but in this case, here, if we look at this in a bit more detail, we will have Q1 going from left to right, and they will be on the same cell segment, will be a Q3 going from right to left. So we have to take that into account, so we have to subtract Q3 here, and similarly, we have to subtract Q2 from that one. Because even though this is cell 1 and has a constant shear flow and a constant torque to it, and therefore constant shear flow due to that torque of cell 1, cell 3 has an effect because they share the same wall. So if you take the rate of twist, basically you have to think about it, just want to deform it counterclockwise, and this cell basically tries to stop it by deforming it in the opposite direction. So this will be a clockwise deformation, and here internally this is counterclockwise, and this one will rotate it clockwise. So that's the reason why that's minus. Okay.
So you're subtracting from one of the A parts and not from the B part?
Yeah, so let's draw that a bit bigger out. So this is cell 1, right? This is the shear flows. Because we have a T1 here, right? Which yields T1 is equal to, Q1 is equal to T1 over 2A, right? A1. And at this side, we have the component of Q3. Q1, 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 Q1. And this side, we have component of Q2. This length was A. This is B. So the integral of this segment is Q ds. So this Q is constant. So the integral becomes Q ds 0 to A, right? And Q you can just write as Q1 because it's a constant. This section is Q, the integral from 0 to B. This is 0 to A because it's the same distance, and this is from 0 to B. And here we have, we assume counterclockwise positive, so this becomes positive, this becomes negative, this becomes positive, and Q2 becomes negative. Okay? And now we can basically substitute the integrals because Q is, the shear flows Q1, Q2, and Q3 are constant. So this integral becomes basically the integral of 0 to A ds becomes S evaluated from 0 to A, which becomes A, right? So this becomes A, this becomes B, this becomes A, this becomes B. So let's write that out. So it becomes 1 over 2 times area 1 GT. And then this becomes Q1A plus Q1B plus Q1A minus Q3A. So I just expanded this bracket plus we get Q1B minus Q2B. And the reason why I expanded it, then we can write down 1 over 2 times A1 continuum purple T, and this Q1A, so we have another Q1A, so we can write this as Q1, 2Q1A plus 2Q1B minus Q2B minus Q3A. So in this case, we cannot, so far we cannot do anything else because basically we have too many unknowns and not enough equations. So we basically have to repeat the same for rate of twist in cell 2. And it will be the same procedure. So I'll give you just the final answer. So that will be 1 over 2 times the area, GT. And then what we get is 2 times Q2A plus 2 times Q2B minus Q1B minus Q3A. And then we do the same thing for the third section or the third cell. Now we get 1 over 2 times area 3 GT. And then we get 4 times Q3A plus 2 times Q3B minus Q1A minus Q2A. Yeah. So now we have 3 equations, and now we can combine those 3 equations and use the basically rate of twist equality. So d theta d z1 must be equal to d theta d z3, 2 in this case, or 3, doesn't matter. And we know that A1 is nothing else than AB, because that's the length and the width. A2 is AB as well, because length and width. A3 is B times 2A, so 2AB. And then let's do one of them. Yeah, basically we said equal d theta dz1, we said that equal to 2. So if these two are equal, we know that A1 is AB, A2 is AB, G and T are equal on both sides, so we can basically ignore this whole 1 over 2A, 1, 3T, blah, blah, blah. Okay. So let's do that. So basically that this segment must be equal to this segment. So we have 2Q1A plus 2Q1B minus 2B 2QB minus Q3A is equal to 2Q2A plus 2QB Q2B minus Q1B minus Q3A. So we can add Q3A out to both sides. So this drops. So this one drops. So we can basically get an equation for Q1 is equal to, or we can get an equality between Q1 and Q2. So let's take all the Q1s on the left hand side, all the Q2s on the right hand side. So we get here plus Q1B, and here we get plus Q2B. And then we can collect Q1 out of the bracket, so we get Q1, then we get 2 plus 3, yeah, 2A plus 3B. And on this side we have Q2, and that's 2A plus 3B. And for this equality to be true, Q1 must be equal to Q2.
So we essentially have 3 equations and 3 unknowns and
yeah. So you have n cells and n number of equations, and then you can solve basically for Q1, Q2, and Q3. And if you do this correctly, so now we have an equality between Q1 and Q2. So we know Q1 is equal to Q2. Then we can set up a similar equation here. In this case, the 2, the G and T will drop out. If you say Q d theta dz2 is equal to d theta EC3. Since we have the same shear modulus and same thickness, they will drop out. However, the area 2 is AB and the area 3 is 2AB. So be careful with that. So the areas do not drop out in this case. And then you can, here you will have Q1, Q2, and Q3. So technically, but you can now substitute Q1 for Q2 or Q2 for Q1, and then you can come up with another equality equation. In this case, you will do Q3 will be equal to Q1. Just happens to work out like that. And then what you can do as last thing, you can go back to our original statement. So I'll do it quickly. This, the solution procedure is elaborated on the lecture slides, by the way. So you have, if you want to go into it yourself, you can have a bit a better look at it. So at the end, we also know that T is equal to T1 plus T2 plus T3. We know that the equivalence is equal to 2 times the enclosed area of 1 times Q1 plus 2 times the enclosed area of 2 times Q2 plus 2 times the enclosed area of area 3 of Q3, right? But from the data from the rate of twist equalities, we've got that Q1 is equal to Q2 and Q3 is equal to Q1. So basically what we can do is collect this. So we get 2 times Q1, then the areas 1 plus area 2 plus area 3. And then if we do this, this is 2AB, 1AB, 1AB. So that's 4AB times 2. So we get 8AB Q1. That's the total torque. So if you want to solve for the Q1, you get that Q1 is equal to the total torque applied divided by 8AB. That will be the last step. So now you have determined what the shear flow is in each cell based on the total torque. Okay. And like I said, the solution procedure is fully elaborated in the lecture slides. I'm going to have a quick look at it. So yeah, this is what we started. We said, like, if you have torsion, the individual torques, if you sum them together, will be equal to the total torque, and the rate of twist must be equal between the different cells. Now we did a quick example. This was example. So we calculated the rate of twist in each of the cells, and then we equate them to each other. We did for cell 1, cell 2, cell 3, and then we state we have 3 equations basically. So we start off by setting Q1 to equal to Q2, and it doesn't matter where you start, if you start with Q2 to equal to Q3 or Q2 to equal to Q1 or 1 to 3, it doesn't really matter. And then we can get an equality between Q1 and Q2, and we got an equality between Q1 and Q3. And then we use that equality to determine what the shear flow equation must be, or the shear flow value must be. And we say that's equal to the torque over the 8 times AB. I think there's a good moment to stop. And then for the next lecture, what we'll do is I will go discuss this example in more detail. So I will recommend you do this at home. Come prepared. So if you have any questions regarding what the difficulties there were, I can address those. And then from there on, we will continue with multi-cell, and then we go to multi-cell shear. And yeah, so we do the shear flow problem and the multi-cell shear flow problem. Okay, thank you. Any questions, by the way? Nope.